Assalamualaikum student. In this video, I will introduce you to the concept of extent of reaction. Okay, this concept is we use this to express the flow rate of each reactive species according to the stoichiometry of the relations that taking place. So the formula to calculate extent of reaction is actually involve this is the general formula, and is number of mole of your species in the output. Okay, sorry, I don't know what to put you. Okay, is equals to number of species at your original initial. So this is initial number of species. This is okay, plus or minus the stoichiometry ratio of your species multiplied by E. So E here is your extent of reaction. Okay, so let me repeat. So Ni here is number of moles your product stream. Okay, this one is the number of moles initial. And you have V here, which is the stoichiometry ratio. And plus minus sign, okay, before the stoichiometry ratio. Plus is when you are dealing with product, and minus is when you deal with the reactant. So we will look at this later. And E is the extent of reaction. Okay, so the concept is almost similar like fractional conversion, but in fractional conversion, the unit is in percentage. But for extent of reaction, you're calculating using this formula, so your extent of reaction, the unit is in mole. Okay. So with this approach, the extent of reaction are solved as part of the solution process. So you are calculating the extent of reaction, to what extent your reactant reacts. So therefore, this approach may be advantage if the question, okay, is asking for you to derive or to calculate the extent of reactions. Right, so let's see the example here. Okay, so we have actually do this example previously in slide 13. Okay, you can refer to the calculation in slide 13 later on. Okay, and here you see you have hydrogen react with bromine to produce 2 mole of hydrogen bromide. So first thing you have to make sure that your stoichiometric equation is balanced. Okay, and it says here at the initial of the reaction 100 moles of hydrogen. You have 100 moles of hydrogen, and you have 50 moles of hydrogen bromide, 50 moles of bromine, and 50 moles of hydrogen bromide were present. At the end of your reaction, only 30 moles of hydrogen react. Okay. So the question asks you to calculate the amount of each species in the product at the end of the reactions. So when the reaction completed using extent of reaction method at the end of the reaction. Okay, and here they give you the most important info that we have here. It says that at the end of the reaction, only 30 moles of hydrogen react. So if initially you have 100 moles and only 30 moles of hydrogen react, so that's mean at the end of your reaction you have 70 moles of hydrogen. Okay, 100 minus 30 is 70. So let's use this formula and calculate for the extent of reaction first. Okay, first you need to calculate for extent of reaction, and later on you can use that formula to calculate for the amount of other species using the value that you calculated for the extent of reaction. Okay, let's see here. So let's see the information that we have is for hydrogen, and H2 is equal to NH2O, initial amount of hydrogen. Okay, I don't want to put it as O. Okay. Let's put it initial here. It's look like H2O, like water. I don't want you to confuse with the symbol here. Okay. Okay, minus because hydrogen is your reactant. Okay. Here, minus if you have reactant and plus if you are dealing with product. Okay, so minus stoichiometry ratio of your hydrogen and multiply with extent of reaction. So, and H2, okay, we know that you left with 70 moles only, okay, because only 30 moles of H2 reacted. 70 is equal to initial amount of hydrogen is 100 mole minus stoichiometry ratio of hydrogen is 1. Okay, here 1 hydrogen plus 1 bromine, you got 2 moles of hydrogen bromide. And extent of reaction is the value that we want to calculate. So your E is 100 minus 70 is 30 moles. Okay. So as I mentioned previously, the concept of extent of reaction is almost the same like fractional conversion. It's just that for extent of reaction, your unit is in mole. Okay. It is, you want to know, you are interested to calculate to what extent your reactant react. So here, you can use this formula and you got E as 30 moles, or even at the statement here itself, it already said that only 30 moles of hydrogen reacted. So here, it already tells you that your extent of reaction is 30. Okay, next we can calculate for the amount of bromine and hydrogen bromide at your product stream using this formula. Okay, so okay, I'll write here, and BR is equals to your initial amount of bromine is, let's 50. Okay, 50 moles minus, is bromine is your reactant, and the extent of reaction is 30. Okay, use the value that we have just calculated earlier. So 50 minus 30 is 20. So at the end of the reaction, you have 20 moles of bromine. Okay, then same thing, you can calculate for hydrogen bromide. So NHBr 2 is equals to initial number of mole of hydrogen bromide is 50 moles. Okay, since hydrogen bromide is the product, so you need to put plus. So be careful with the sign here, okay? And you have 2. The stoichiometry ratio is 2. So make sure you put number 2 here. And the extent of reaction is 30 moles. Okay, so 50 plus, okay, 2 times 30 is 60. 60 plus 50 is 110 moles of hydrogen bromide. Okay, so we have solved for this equation, this problem. So at the end, you have 70 moles of hydrogen, 20 moles of bromine, and 110 moles of hydrogen bromide. So let's check this answer with slide 13. Okay. Okay, you have 70 moles of hydrogen, 20 moles of bromine, and 110 moles of hydrogen bromide. So this equate, earlier you used the method of fractional conversion. Okay, not really fractional conversion, but you using this general mass balance equation. But now, see, you are actually, we use the extent of reaction method where we calculate for the extent of reaction and use that this formula to calculate for the amount of each species had a product stream. Okay, now let's look with this example. Okay, we have also done this example in slide 14 without the external fraction. Now I want to show you how to solve this problem using external fraction. Okay, acetone nitrile is produced in the reaction of propylene, ammonia and oxygen. And they give you the chemical equations here. Okay, so I don't want to focus on the calculating on the limiting reactant, identify it. That is the same method. So previously we have compared the number of moles given with the stoichiometry ratio, and the limiting reactant is your propylene. Okay. Okay, percentage by which each other reactant is an excess. We have done this before. Okay, once you know the limiting reactant, so the other reactant must be an excess. So you just calculate the excess. Okay. Next, okay, the molar amounts of all product constituent for a 30% conversion of the limiting reactant. So now we want to calculate the molar amounts of all product of gas for 30% conversion of the limiting reactant. So let's see here. So your limiting reactant is propylene. So you have okay, let's write the equation. Is equals to NC3H6 initial minus stoichiometry ratio multiply with extent of reaction. Okay, so if your fractional conversion is 30%, so it means that the balance, okay, is 70%. Okay, so 0. Okay, here and C3 H, H6 is equal to 0.7 multiply with the initial amount here, okay, where you have 0.1 moles of C3H6 per mole multiply with 100 mole of feed. So NC3 propylene is 7 mole. Okay. So here you have 7 mole equals to initial is 10. You can write 10 directly, or you can write 0.1 mole C3H6 per mole multiply with 100. So I just you can write like that, or you can direct write 10 mole. Okay. Minus extent of stoichiometry ratio. So minus because it's your reactant 1. So here your E is 3. Okay, 3 mole. 10 minus 7 is 3. Okay, so now let's solve for the other species. So NH3 is equals to, the initial value of NH3 is 12 mole minus, so let's check, NH3 is 1, so 1, and the extent of reaction is 3 mole. So 12 minus 3 is 9 mole. Okay, then same thing, repeat for oxygen. So oxygen 0.21. Okay, it's better to write it down here. 0.21 mole of O2 per mole air. I want to write this time because if I directly show excuse me, directly show the value that I calculated, you don't see the calculation method, how to get that value. Okay, multiply with 0.78 mole air per mole of feed. Okay, then multiply with 100 moles. Okay, so this is the initial value, and you will get 16.4. Okay, 0.21 multiply with 0.78 multiply by 100. Okay, minus here. Okay, take note, you have 3/2. And your E is 3 moles. So it's 60.4 mole minus, okay, 1.5 multiply with 3 moles. So you will get, at the end, you will get 11.9 moles of oxygen at the end of the reaction. Right, so next is for acetonitrile. Okay, so from the questions, okay, you don't have acetonitrile at your input, so 0. The first term is 0 because you don't have anything. And let's check for the stoichiometry ratio. It's 1. Okay, so plus 1 E. Okay, so your extent of reaction 3 is 3 mole. So your number of mole of acetonitrile at the end of the reaction is 3 moles. Next we have water. So let's see if you have any water at your input. So no, you don't have water at your input. So the input number of mole, initial number of mole for water is 0. And you have 3 here for the stoichiometry ratio, plus 3. Okay, so 0 plus 3 E. Okay, so 3 multiplied with 3 is 9. So at the end of the reaction, you have 9 moles of water. Okay, last one is, we have this, we have this, we have this, and this. Last one is for nitrogen. And N2. So you have to keep in mind that nitrogen is inert gas. So it does not involve in the reaction. So you don't have to calculate with, you don't have the E here. Number of moles of nitrogen at the output must equal to number of nitrogen at your input. So at your input you have this, okay, 0.79 mole of nitrogen per mole air. So you calculate it, 0.79 mole N2 per mole air, 0.78 mole air per mole 100. Okay, so the number of mole of nitrogen at the product, like I said before, is the same, like is equal to the number of mole of nitrogen at your input. So here you have 61.6 mole of nitrogen. So let's compare the answer here with slide 14. Okay, H2O is 961.62. Okay, 3 for acetonitrile, 11.9 for oxygen, and for ammonia you have 9. So the answer is the same. Okay, with both method. Alright, so we stop until here for Axenov reaction topic. Alright, in next video we'll continue with another topic. Alright, thank you.